तो यूनिट्स ऑफ कैपेसिटेंस के बारे में हम बात कर रहे थे, तो यूनिट्स ऑफ कैपेसिटेंस जो है फैरेड होते हैं. तो जैसे Q इज इक्वल टू सी वी है, तो C इज Q बाई V. दैट मीन्स कैपेसिटेंस जो है दैट इज चार्ज अपॉन पोटेंशियल. राइट. तो 1 फैरेड इज इक्वल टू 1 कूलम बाय 1 वोल्ट. तो फैरेड इटसेल्फ बहुत बड़ा यूनिट है. So we cannot take it as we cannot use it, because 1 farad is a huge amount of capacitance. For that, to store that much charge, we need a sphere of radius more than that of Earth. So we use the smaller units like millifarad, microfarad, picofarad, nanofarad, like that. Millifarad means 10 to the power minus 3 farad, and microfarad is 10 to the power minus 6 farad, and picofarad is 10 to the power minus 12 farad. And now suppose we want to, let's say, find the capacitance of an isolated spherical conductor of radius, say, R. So general formula we can find out. Let us say there is a sphere of conductor of radius R. Right? And the charge is located on its surface outside it, which is plus Q. This is charge is plus Q all over this conductor. Right? Radius is R. So V is the potential. That means this charge is uniformly distributed over this whole sphere. Fine. And now the potential at any point on the surface of this sphere is given by V is equal to 1 by 4 pi epsilon naught. Q by R is the formula for that. So charge is Q upon R. Right? And capacitance is equal to, we have charge directly proportional to potential, or charge is equal to CV, where C is the capacitance, and C is equal to Q by V. Right? So we have C equal to Q upon, this is 1 upon 4 pi epsilon naught, putting the value of V over here, into Q by R. So that will give me, this Q will get cancelled with this. So C is equal to 4 pi epsilon naught R. This is the formula for this, right? Capacitance. Fine. Now we can see this capacitance is directly proportional to the radius of the sphere or spherical conductor. Now we can find the value of this R, radius. So radius is equal to, say, C by 4 pi epsilon naught, or we can write it as 1 by 4 pi epsilon naught into C. Right? So this 1 by 4 pi epsilon naught is what? 9 into 10 to the power 9 Newton meter square per coulomb square. Right? And C we want, say, 1 farad. So R will be equal to 9 into 10 raised to power 9 meter. This is the radius of a sphere in which 1 farad of capacitance is there. So which is much more than the Earth. Radius of Earth is 6.4 into 10 to the power 6 meter. And this is 9 to 10 raised to 9 meter, approximately 1500 times more than that. Right? So it's a large unit of capacitance. So that is why we don't use it. Then capacitor, how do we store the charge in that? And if we place, say, any conductor, earth the conductor near it, then the capacitance of a capacitor plate increases. Let's say there is one charge plate at a plate A, and an uncharged plate B is placed close to it. Fine. So let us say we have so this is plate A with positive charge. And here we place another plate B. Now, plate A is having a positive charge, fine, on both sides. So due to induction, it will induce a negative charge on the inner face of the plate B. And positive will be there. Right? Due to induction, the face of plate B, which is closer to the plate A, acquires the negative charge. Right? And this face, which is away from plate A, acquires the positive charge. The negative charge is there on plate B. It tends to reduce the potential on plate A. And positive charge on plate B tends to increase the potential on plate A. So negative charge of plate B, which is closer to plate A, than the positive charge. So the net effect is that the potential of A will be decreasing. It decreases by a small amount, and hence the capacitance increases by a small amount. Because whenever this potential decreases, capacitance increases. Like here I am having a bottle. So, and there is a, say, rubber band, which might be, man, is this visible, this rubber band, yellow one? Right? So if I increase the position of rubber band from, like, say, let's say it's at this point, the potential will be this much. And if I lower it, say this much, the potential is reduced. And let's say we can, the capacity to hold water is up to this rubber band only. And here the charge is this much, up to this level only. And if I place it here, charge can be filled in this up to this. Means the potential increases, the charge can be stored more. Right? And we have the formula as charge is equal to C times V, or capacitance is equal to charge by V. These two are inversely related. This is the potential. If it is reduced, then this much space is still available for the charge to be filled in it. That means the capacity increases. Similarly, if this is attached to, say, earth, then continuously flow of negative charge will be there from earth to the plate B, and plate B will acquire some negative charge on it on both the sides, which reduces its potential further. And when the potential is reduced, the capacity to hold charge increases, because we can pour more charge. More charge can be flowed into it. Right? So capacitor depends upon shape, size, and relative position of two conductors. And it also depends upon the nature of medium between them. So capacitor जो है, it is an arrangement of two conductors, like it's shown here. Two conductors which are separated by some distance or by some insulating medium that is used to store electric charge and electric energy. And it is represented as two parallel plates, symbol of the capacitor. And it is like this, right? That variable capacitance is there. Fine. So most important is the parallel plate capacitor. The regular, the simplest and the most widely used capacitor is parallel plate capacitor. So it has, let's find it, how much capacitance it can have. Parallel plate capacitor, right? So let's say there are two plates. Fine. Two plates which are having an area of cross section say A, and the distance between them be say D, separated by distance D. Right? And we have a surface charge density sigma. Fine. So here it is a plus charge. Let's say. Fine. Upper region is of the upper plate. Fine. This is say plus charge. And total charge will be Q, that is sigma times A, because this is surface charge density, and total charge is equal to sigma times A. Fine. That's the total charge on each plate. Now, outer region में, here it is negative, reduced. So electric field is shown. Electric field will be there. Fine. Charge is, this is like positive to negative. And E is always, we know, sheet of charge is there. Electric field will be sigma by epsilon naught. Between these two plates, it will be sigma by epsilon naught. In the outer region, above this plate and below the lower plate, above this plate and below the lower plate, the electric field due to two charge plates would cancel out, and net field will be zero. Like here we have sigma is equal to E is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught. So outer region of above this plate and negative plate is this, so below this region. So this will be sigma 2 epsilon naught minus sigma by 2 epsilon naught, which is, they are opposite and equal to each other, they would cancel each other, zero. Now in the inner part, inner region of this, in the inner region, between these two capacitor plates, electric field due to two charge plates will add up. So that means E will be equal to sigma by 2 epsilon naught due to one plate plus sigma by 2 epsilon naught due to other plate, which gives us sigma by epsilon naught. So this is the electric field between the two plates, sigma by epsilon naught. Right? Sigma by epsilon naught is this. And the direction is always from negative to positive. It is shown over here also. It is negative to positive. It is uniform throughout because the plates are placed parallel to each other, right? And for those plates which have infinite area, the field lines, they may bend at the edges only, but we are considering the plates to be parallel, right, of finite area. So simply we'll do this. Now, and for a uniform electric field, there must be potential. This gives rise to the potential difference between the two plates, and that potential difference is equal to the electric field and the distance between the two plates. That means V is equal to E into D. V is equal to ED. Now, what is E here? We have sigma by epsilon naught. So V is equal to sigma by epsilon naught E into D. E D. Right? And capacitance कितना होगा? Capacitance E is equal to Q by V. Right? So what is the charge we have? Sigma A. This is equal to sigma A upon sigma D by epsilon naught. This sigma goes with this. So we have P is equal to epsilon naught A times upon D. This is the formula of a capacitance of parallel plate capacitor. As we can see, this capacitance is directly proportional to the area of cross section. It is directly proportional to the permittivity of the medium between the plates, right? And it is inversely proportional to the distance between the plates. Right? Now, if some dielectric medium is placed in it, right? Suppose a dielectric material of dielectric constant, say K, is placed in between. Then electric field will be 1 by K times this, right? That is equal to sigma upon K epsilon naught, right? And charge, we have sigma times A, right? So electric field will be right, charge on each plate is Q, and area we have is what? A. So this sigma is Q by A. So electric field can be written as Q upon K epsilon naught A, right? And we know E जो है, this is V by D. As we have done here, that potential difference is equal to electric field into distance. V is equal to E D or E is equal to V by D. Now let's equate these two equations. So on equating, we get V is equal to let's say V by D is equal to Q K epsilon naught A, or V is equal to dq upon K epsilon naught A. Right? Now we need to find the capacitance. This is potential difference. So potential capacitance will be C is equal to what? Q by V. Q by V. So C equals to Q upon D Q. This will move up. So K epsilon naught A, Q goes with this. So we have C equal to K, which is dielectric constant of the medium, E permittivity of the free space, A upon D. Right? This much farad is the capacitance. for any material when placed between the two parallel plate capacitors. Right? Now, let's move ahead. We'll do combination of the capacitance, how these are connected to each other. We can combine them in series as well as in parallel. See, when the negative plate of one capacitor is connected to positive plate of the second capacitor, and the negative of second is connected to the third, then we can say that capacitors are combined in series or connected in series. Like series combination of capacitors. So, the positive charge is there, let's say plus Q, it will induce negative charge on the other plate. Again plus Q, this is minus Q, plus Q, minus Q, right? So we have positive charge over here on this plate, negative over this. Positive, negative, positive, negative, right? So it is attached to some source potential. V is across this combination, right? Now, the potential difference across the various capacitors. This will be the sum of, like it will be V1, this is V2, this is V3. So total potential difference will be equal to sum of the V1, V2 and V3. Right? So we know this charge remains same in series combination as when positive charge, it induces a negative on the other plate, then it moves to the positive, then negative, then positive, then negative. The magnitude of the charge remains same. Right? So V is Q by C. This is Q by C1. This is Q by C2. Q by C3. Q is common factor. We have 1 by C. That means equivalent capacitance is equal to 1 by C1 plus 1 by C2 plus 1 by C3. You must have seen this relationship amongst the resistors, but this in case of resistors, they are connected in parallel, then we get equivalent resistance like this, the reciprocals of these. But in capacitors, they are, when they are combined in series, then the equivalent capacitance or the reciprocal of the equivalent capacitance is equal to sum of the reciprocals of the individual capacitances. And the value of the equivalent capacitance is always less than any of the capacitors. Right? The charge on each capacitor remains same when they are connected in the series combination, and the potential difference and across any of this capacitor is inversely proportional to the capacitance. Right? So we can say this is Q by C. Fine, it's done. Then we have parallel combination. So in case of parallel combination, positive plates of the capacitor, they are connected to one common point, and like this. These are positively charged plates, these are negatively charged plates, positive, negative, positive, negative, positive, negative. Okay. They are connected to common point, one common point, and negative to the other side, right? So when they are connected to the potential, here potential difference applied across these combination will be same. All the capacitors will have a common potential difference V, but potential difference is given by we know the total charge will be is to be, so this is say plus Q1, this is minus Q1. Then comes the Q2 and Q3. Minus Q2 plus Q3, this is minus Q3. Right? So total charge which is in this plate is given by CV or C1V. The total charge which is stored in the conductor combination of these capacitors, that is equal to Q is equal to Q1 plus Q2 plus Q3. Right? Then Q is equal to Q1 plus Q2 plus Q3. Putting the values, we have Q1 will be equal to P1V, as they have the common potential. We have C2V plus C3V. This CV. So V is common factor again. Then CP, that is C1 plus C2 plus C3. The equivalent capacitance is always equal to the sum of the individual capacitances in case of parallel combination, right? And the value of the equivalent capacitance is always greater than the largest individual capacitance, right? The potential difference across each capacitor remains the same, whereas the charge remains same in case of the series combination of the capacitors. Here the potential difference across each capacitor will remain same. The charge on each capacitance is always proportional to the capacitance. Based on this, there are numericals also. So let us first done with the theory. Only one part is left, that the energy stored in this. Let's do that, and then we can solve the numericals. Now, first we'll find the energy stored in a capacitor. So capacitor, we know it's a device which is meant to store energy, and the process of charging up capacitor involves the transfer of electric charges from its one plate to another. While doing so, we have to do some work, and the work done in charging the capacitor is stored as its electrical potential energy. And this energy is supplied by the battery at the expense of its stored chemical energy in it. Right? Now, let's find the expression of this. Let us consider a capacitor, parallel plate capacitor C of capacitance C. So initially we'll consider that the two plates of the capacitor, they are not charged. Fine. Then so let's take parallel plates. Fine. Two plates are uncharged, and suppose some positive charge is transferred from plate 2 to plate 1. So let us consider this plate be 1, this plate be 2. Fine. The positive charge is transferred from plate 2 to plate 1, and in this process, external work has to be done. Fine. So two plates are uncharged, right? The positive charge is transferred to this, so it will be given negative here, positive over here, right? Then this is a Q dash, let this be Q dash, right? They have charges. Plate 1 has Q dash, and plate 2 we have say negative charge over here, like this. Fine. The potential difference between the two plates will be potential difference between the two plates will be V dash. This is equal to Q dash by C, right? This is Q dash by C. Wait a minute. Okay. Right? And let's say some minimum charge, additional charge rather, dq dash be transferred from plate 2 to plate 1. Right? So minus dq is the charge which has been transferred from plate 2 to plate 1. Right? Then work done in doing so will be equal to, we know work done W is equal to V into Q. V is the potential difference and Q is the charge. So work done will be dW, that is equal to charge is dq dash and potential is V dash. So V dash into dq dash. And what is the value of V dash? This is dW is equal to Q dash by C into dq dash. Total work done can be found by transferring a charge Q from plate 2 to plate 1. Fine. This is equal to integrating this W. Fine. This is equal to integration dW. That's what total work done. This is integrating dW from initially it was not charged, 0. Now it's fully charged Q. That is, we have value of Q dash by C into dQ dash. Right? So 1 by C is constant, it will be taken out. Fine. So integration of Q dash, this is equal to, excuse me, So we have Q dash, Q is equal to power 1 plus 1. This is dash. Power is 1. 1 plus 1 is 2 upon 2. Right? Then from 0 to Q. Now putting the limits, we have work done W is equal to half Q dash Q square by C minus 0. So it doesn't make any difference. So this is the work done, which will be stored as electrical potential energy, half Q square by C, right? And when it is stored in the form of electrical potential energy, we replace W by U. U is the electrical potential energy. Q is again C. So we can write it as half C square V square upon C. C gets cancelled with this. This is equal to half CV square. Another formula. Or we can use half CV square is this. Q is equal to CV. And half QV. This half CV square U is equal to half CV into V. This CV is equal to Q, so U is equal to half QV. This is the formula. This is one formula, and this is another. So this is the amount of work done which will be stored in it as its electrical potential energy. Right? See, when several capacitors they are connected in series or parallel, the energy stored would always be additive in either case. Means, suppose there is a series combination of capacitors. So we have Q constant, that means charge is constant. So potential energy will be equal to Q half Q square by C. This Q will remain constant. Fine. So 1 by C we have calculated as 1 by C1 plus 1 by C2 plus 1 by C3. Let's say in series combination, in series, Q is equal to half Q square by C. So this 1 by C can be written as Q square by 2. So 1 by C1 plus 1 by C2 plus 1 by C3. Right? Or when we open this bracket, we can get Q square by 2C1, Q square by 2C2, Q square by 2C3, and which is nothing but potential energy. Fine. So this is U is equal to U1 plus U2 plus U3 in case of a parallel combination. In case of series, this is in series. Now in case of parallel, what do we have? Right? So parallel means in series Q is constant, and in parallel we have V constant. Vs constant. Right? So energy given is U is equal to half CV square. Right? The C can be written as V square by 2, C1 plus C2 plus C3. So U is equal to V square C1 or C1 V square upon 2 plus C2 V square upon 2 plus C3 V square upon 3. This is nothing but U1. So U is equal to U1 plus U2 plus U3. So in either case, whether series combination or parallel combination, energy stored is additive in nature, right? Energy stored is additive in nature. And we need to do some numericals, but I think time will not permit us today. And there is just one topic is left. What is the dielectric constant and all that. So we can do it tomorrow. We'll do it tomorrow. So there's one topic when some conducting slab is placed in between the parallel plate capacitor, what effect it makes, right? That's the only topic we are left with. Rest is not there. Yeah. So we are left with only one topic, which will be done tomorrow. Energy stored in a capacitor, we have done.